are in a galaxy. So this is a galaxy, and it maybe has 100 billion stars. And about once every 100 years, a star in that galaxy will explode like this. And when it explodes, it's extremely luminous. And so we can use it as a standard candle because the further away it is, the fainter it will appear. To be a little more quantitative about it, the light obeys the inverse square law. The brightness declines as 1 over the distance squared. And so if you find one of these objects that's twice as far away, it'll be 4 times as faint. If you find it 3 times as far away, it'll be 9 times as faint. So by finding these standard candles, we can measure distances throughout the universe. Now, the other aspect we needed to measure from that animation was the apparent motion of objects like galaxies away from us. And so we can also measure this with standard candles. In this case, it's not the brightness of the light, but it is a shift in the wavelength of the light. So phenomenon in the universe emit light at certain known wavelengths. Wavelengths of light we can determine in the laboratory from different transitions. But then as to us, the universe expands. And so that light, the wavelength, is stretched to the red. That is, it's red shifted by the time we receive that light at our observatory. This might remind you of the Doppler shift. It's not exactly the same thing. In the Doppler shift, it's actually the physical interpretation is that the other object is moving with respect to us. In this case, neither is moving, but it's actually space that is expanding. And this is an important distinction because it gives you a different picture of what's actually going on. I like to think of this as if you watched somebody walking in the airport at some speed, you would understand that they are walking, they're moving. But if you saw a bunch of people all standing together and you couldn't see them below the knee, but they were all moving at the same speed, you might realize they were on one of these people movers, these conveyor belts, right? You see the same phenomenon, but in the latter case, you have a different understanding of what's going on because there will be a whole pattern of motion which is different than just an individual object moving. So we measure the apparent recession of objects measuring the redshift. And so by seeing both the brightness to determine the distance and the shift in color, we can determine how far away and how fast something is moving. Get rid of this here. Oops, sorry. Okay. So now we can get more quantitative about this. We can go out and look at that pattern of galaxies around us. We can measure how far away and how fast they are moving, and seeing a linear relationship between the two is the signature of an expanding universe. It means that the further away something is, the faster it is moving away from us. That's what will happen in an expanding universe, or that loaf of rising raisin bread. And we can go further. We can measure the slope of this relation to tell us what the expansion rate of the universe actually is. If the universe were expanding faster, it would be a steeper slope. Less fast, a shallower slope. If the universe were contracting instead of expanding, we would have a negative slope. That is, we would mostly see blue shifts around us. And so this is known as Hubble's law, that there is a linear relationship between the velocity and the distance. And by measuring that quantity relation, we can determine how fast the universe is expanding. Now, this is not just a thought experiment. This was actually measured first by the American astronomer Edwin Hubble in 1929. He was on the 100-inch telescope at Mount Wilson, and he combined distance measurements with redshift measurements from the astronomer Vesto Slipher about a decade earlier. And he was able to make this very iconic graph. This plot of distance versus redshift that shows this linear relationship, this is the first indication that the universe is expanding. And it's so iconic, it's so profound. I don't have any tattoos, but if I got a tattoo, I think I would get this because it's that meaningful in terms of our understanding of our place in the universe. So for my thesis, I was able to follow up on that work by measuring even further out. And so here is another one of these, what we now call a Hubble diagram after Edwin Hubble, where all of his original measurements would fit in this tiny little red square in the little corner over here, but we were able to go much further out with the supernovae, and you could see the universe continues to expand as we look further and further out. Okay, so you understand the universe is expanding, and you understand we can measure the rate at which it expands. Now we can begin to address some really interesting questions about the universe, like when did it all begin? And the way we do this is as follows. We use this fact of the expanding universe, that galaxies are separating and that we have measured the rate, known as the Hubble constant, to imagine turning that movie of the expanding universe backwards in time. We run the movie backwards in time. Okay, that is to say, instead of the universe expanding, we imagine the universe contracting at that same rate, and we ask, how long do I have to run that movie backwards until everything is on top of everything else? It's a little like watching a marathon race, and you catch somebody running at mile 20 at a certain speed. And knowing they're at mile 20 and gauging the speed they're at, you can figure out when the race started, assuming that they haven't sped up or slowed down. And so we do the same thing. We assume for a moment that the expansion rate has not changed over time, and we're able to find out how old the universe is. It turns out it comes out to about 1 over the Hubble constant. Now, in 1929, when Hubble first measured this expansion rate, he got a number that was so large that it implied the universe was so young, about 2 billion years old. Now, even in 1929, we knew that that was not correct. We knew the Earth was older than that. The dating of radioactive isotopes in the Earth's crust told us that. However, we learned that we had a lot to learn about measuring the rate at which the universe expands. This was a nice graphic made by the New York Times a few years ago on this 100-year quest to measure the rate at which the universe expands. So here's Hubble's initial measurements and the implied age of the universe. But then over the last 80 years, the values have come down dramatically as we've learned a lot about the universe. We learned that there are different kinds of stars, different populations. It's almost like mistaking one kind of lighthouse for another kind of lighthouse. We developed new technology. We launched the Hubble Space Telescope. We learned to measure distances to supernovae. And so an interesting thing has happened just in the last 10 years. There's been a great convergence on the measurement of the expansion rate of the universe. And it comes down to a number which tells us that the universe is about 13.4 billion years old. That's comfortably older than even the oldest stars in the universe. So we have made a great deal of progress on at least figuring out how fast the universe is expanding today. But you might be wondering, well, what happens next? What is the fate of an expanding universe once it's expanding? A very similar question was asked by Isaac Newton of himself. What happens when you fire a cannonball off of a mountain? You could fire it with greater and greater velocity, and that cannonball will get further before it falls to the Earth. If you fire it with enough velocity, it will go into orbit, or even more velocity, it will escape the gravitational pull of the Earth. Now, this depends not just on the velocity of the cannonball, but on the mass of the Earth itself. So if you already saw the cannonball in flight and you wanted to know if it would fall back, you would have to know the mass of the Earth. And as the physics students I talked to today in the mechanics class may have learned, by measuring the deceleration of the cannonball, they could also figure out how much the Earth weighed and whether that cannonball would fall back to the Earth. So this is very analogous to the question we had about the universe, which is, okay, there's all this matter in the universe. Surely that is acting like a brake on the expansion. The gravity is slowing it down. Will it slow down and stop? Will it start contracting, or will it expand forever? That is, does the universe have escape velocity from itself? Now, 100 years ago, Einstein thought about this problem as well, but he thought about it in a different way. It turns out that in 1916, just about 100 years ago, he was told by astronomers of his day that the universe was static, that it was neither expanding nor contracting. And this was a real puzzle to him. He had just developed a new theory of gravity called general relativity. And he realized in that theory of gravity, or even in Newton's theory of gravity, that if you had a configuration of objects that were motionless, that were static, and then you let go of them, that the attractive gravity from all of them would cause them to start to collapse. And yet he was told the universe was static. So there must be something balancing the tendency of the universe to collapse. And he made a remarkable discovery. His remarkable discovery was that in his theory of gravity, while the gravity of matter in the universe was attractive, the gravity of empty space itself could be repulsive. And he thought this gravity of attractive stuff and repulsive gravity of empty space could be in a perfect balance, holding the universe static so that it was neither expanding nor contracting. Now, he called this property of space the cosmological constant. Today, we would call it dark energy. But as I said, it was initially invoked 100 years ago as a feature of Einstein's theory to keep the universe static. Now, some 10 years later, Einstein learns from Hubble and others that the universe is expanding and realizes that he never needed this stuff, this dark energy or cosmological constant in the first place. He actually goes and visits Hubble. Here he is visiting, here's Hubble, here's Einstein at Mount Wilson in 1931. And to be really sure about this, he goes to the telescope, apparently. This must be a PR photo because even at the time, Hubble was observing objects so faint that you needed a photographic plate and a 1-hour exposure to see them. So there's no way with his eye that Einstein could see anything, but he's a theorist. So, who knows? Maybe he doesn't know that he should see something. Nevertheless, apparently this was enough to convince Einstein that Hubble was really right in his craft and had measured this fact about the universe. So Einstein famously refers to this as the biggest blunder he made to come up with this cosmological constant. Okay, so how can we then measure if the expansion rate is slowing, just like that cannonball shot from the mountain? How can we measure the deceleration and determine whether the final trajectory is one of recollapsing or expanding forever? Well, most things we want to know how they're doing. We wait a while, like the economy. You see how it does next quarter and the quarter after. But the universe evolves very slowly, so we cannot wait to see how the universe changes. But what we can do is take advantage of an interesting, really a trick in the universe. And this trick is just the realization that the information we get from the universe is delayed information. That is, I like to say the universe does not instant message. All the information we get comes from long ago. So, for example, if we look at a distant standard candle, we're getting information about the universe, not the way it is today, but the way it was a long time ago. Specifically, a long time ago, the distance away to that object divided by the speed of light. So a typical supernova might tell us how the universe was expanding 1 billion years ago. Then we can go out with our telescopes and look for an even more distant one. That would tell us how fast the universe is expanding maybe 2 billion years ago. Even more distant, maybe 3 billion years ago. And so we can look at the changes in the expansion rate of the universe. That is, we can still see with our telescopes the whole growth history of the universe just by looking out. We're looking back in time. And so this is a powerful way to see if there have been changes. So in the mid-1990s, the expectation was if we did this, we would see that the universe resembled either the model on the left or the model on the right. The model on the left is a very heavyweight universe. It's one that started with a big bang, grew in size, but eventually will be overwhelmed by the gravitational attraction of all the matter in it. It will be decelerating the whole time, reach a maximal relative size, and then it will begin to collapse and end in a big crunch. Or we could have lived in a lightweight universe, one that there's very little matter, there's very little deceleration, the universe just keeps growing and growing. That is, the universe has escape velocity from itself. Or we could have lived on the knife edge case just exactly between those two, where the universe has exactly escape velocity. And so it was thought that by measuring the amount of deceleration we've seen of the expansion of the universe, we would in essence be weighing the universe and figuring out what its ultimate fate was. Now, it turns out not any kind of supernova will do as a standard candle. There's a particular class of supernovae called the Type 1a supernova. And the phenomenon behind a Type 1a was first, I would say, explained or understood by the famous Indian astrophysicist Chandrasekhar in the 1930s. And Chandrasekhar showed that there is a certain critical mass known as the Chandrasekhar limit for the mass of a star in a state known as a white dwarf. When a star, and the sun could become a star like this, a white dwarf, reaches 1.4 times the mass of the sun, it's at that critical state. If you add just another teaspoon of material onto it, then it will no longer be able to hold back the crushing force of gravity, and you get a runaway thermonuclear explosion through the whole star. Now, we think this happens on a regular basis when a star like that is in a binary. There are two stars orbiting each other, and if they get close enough, perhaps the other star swells up at some point, mass is transferred over until this white dwarf crosses the Chandrasekhar limit. So this gives us a very uniform explosion, a very good standard candle. Reaches a peak luminosity of about 4 billion times that of the sun. You could see those halfway across the universe with the Hubble Space Telescope, maybe 2/3 of the way across the visible universe. And then the explosion can be witnessed for months as the supernova is powered by radioactive decay. Okay, so you might wonder, how do we find these supernovae? These are 4 that I collected in my thesis in 1995, these bright spots, and here are the background galaxies. So how do we find these? It's actually pretty easy. You just look for the bright spot at the end of the arrow in the pictures. No, we add the arrows actually in Photoshop. You have to find the supernova by some other means first. The way we do it is we use a way of skewing the odds in our favor to find a supernova. See, a supernova is a rare event. It's like winning the lottery. You only expect it to happen once every 100 years in a galaxy like ours. So if you pick your favorite galaxy and stare at it, you have to look at it a long time before you're liable to find a supernova. This is not going to work very well. However, you also realize that means you could observe 100 galaxies all at the same time over the course of a year. Then you'll probably find a supernova. So this is like winning the lottery by buying all the lottery tickets. You know, you have bought so many chances, you're sure to win. And we go much further than that. You could look at 1,000 galaxies to find 10 supernovae in a year, or that picture I showed you at the beginning where there were 10,000 galaxies. That picture will yield 100 supernovae this year. So that's one every few days. And we go even wider or bigger than that. So we can find them on demand by taking wide enough images. And then we use computers to help us analyze those images, to subtract one image from a new image. So here's an image of the sky. Here's one taken a month later. We digitally align them, subtract them, and the computer is good at alerting us to the fact that there's a new point of light in an image like this. So in the mid-1990s, we formed a team, the High-Z Supernova team, that planned to go out and find more distant supernovae, measure how fast the universe was expanding in the past, compare it to how fast it's expanding today, to see how much deceleration there was, and in essence, weigh the universe and determine its ultimate fate. Now, by 1997, in the fall, I was fortunate to be leading an analysis for our team of our first large set of about 16 of these very distant supernovae. And I was assuming that there was just a simple correspondence between how much deceleration there was in the universe and how much mass was in the universe, in the funny units that astronomers use, neglecting this cosmological constant. I mean, Einstein had thrown it away. Who am I to bring it back? And I wrote a simple computer program to use the deceleration as witnessed by the supernovae to tell me what the mass of the universe was. And when I got results from that, and here's a key page from my lab notebook, I was stunned. It didn't make any sense. I was expecting for the mass to either be a small number or a big number, and instead I got a negative number. Now, that's bad physics. There's no such thing as negative mass, but computers don't really know physics. Computers just know the equation you put in, and they try to make that equation work. And so in my case, I hadn't yet realized that the universe was not decelerating. It was actually accelerating. The sign was different, and I had not given the computer enough physics to possibly explain that. So it did a silly thing. It said, okay, let's pretend mass is negative. Now I could fit the data. But what that really meant was that something like Einstein's term, Einstein's cosmological constant, really should not be neglected, and in fact was dominant, was the thing that was probably explaining what was going on. So a few days later, I contemplated how likely was this to be the case, did some calculations, and concluded that yes, statistically speaking, the data required something like Einstein's cosmological constant, or more generally, dark energy. Now, having reached this point, I began talking to the other members of my team because we needed to do a lot of cross-checking. We were very worried that we had made a mistake, a simple computational error or something. This happens all the time in science. And then within a few weeks, we entered into an email discussion with these colleagues who were spread over 4 different continents. And over one 24-hour period, it's quite interesting to read what the email discussion was like when they were first learning about this result. So I had been at UC Berkeley at the time, and Alex Filippenko, the professor I was working with there, sent an email to the team on January 10th, 1998 at 10 a.m. Adam showed me fantastic plots before he left for his wedding. Our data imply a non-zero cosmological constant. Who knows? This might be the right answer. Bruno Leibengut, who was based in Germany, responded immediately. Concerning a cosmological constant, I'd like to ask Adam or anybody else in the group if they feel prepared enough to defend the answer. There is no point in writing an article if we are not very sure we are getting the right answer. So you can see scientists are very conservative by nature because most new things are wrong. But Brian Schmidt, my colleague who had been responsible for finding the supernovae, was in Australia and responded, I agree our data imply a cosmological constant, but how confident are we in this result? I find it very perplexing. Bob Kirshner, who was my thesis advisor, he was on sabbatical at the time in Santa Barbara, responded, I am worried. In your heart, you know the cosmological constant is wrong, though your head tells you that you don't care and that you're just reporting the observations. It would be silly to say we must have a non-zero cosmological constant only to retract it next year. Mark Phillips in Chile responded, as serious and responsible scientists, we all know that it is far too early to be reaching firm conclusions about the value of the cosmological constant. John Tonry in Hawaii responded, who remembers the detection of the magnetic monopole and other gaffes? On the other hand, we should not be shy about getting our results out. Alex Filippenko writes back again, if we are wrong in the end, then so be it. At least we ran in the race. There was another team at Lawrence Berkeley National Lab just up the hill that we knew had their own data and was working on a similar analysis. So there was a feeling of competitiveness and not wanting to be second if there was something interesting. I got back from my wedding, packed my bag for my honeymoon, quickly snapped off a response. If we're wrong in the end, then so be it. At least, oh, sorry, that was Alex. The results are very surprising, shocking even. I have avoided telling anyone about them because I wanted to do some cross-checks. I have, and I wanted to get further into writing the results up. The data require a non-zero cosmological constant. Approach these results not with your heart or head, but with your eyes. We are observers after all. Alejandro Clocciati, my colleague, another colleague in Chile, wrote, if Einstein made a mistake with the cosmological constant, why couldn't we? I never knew if that was supposed to be reassuring or not. Never have figured that out. Nick Sunsef in Chile responded, I really encourage you, Adam, to work your butt off on this. We need to be careful. If you are really sure that the cosmological constant is not zero, my God, get it out. I mean this seriously. You probably never will have another scientific result that is more exciting come your way in your lifetime. And of course, Nick was right. So after careful work, we put out a paper, Observational Evidence from Supernovae for an Accelerating Universe and a Cosmological Constant. And the other team reached the same conclusion and wrote a very similar paper. Both teams were basically saying that the universe is now accelerating, implying that 70% of the energy mass budget of the universe is in this mysterious form of dark energy. So this became the breakthrough of the year for Science magazine. Apparently, even Einstein would have been amazed. There's him blowing bubbles with his pipe. That this idea, this aspect of his theory, this sort of last part that had never been seen before, actually seemed important. So why is it that the universe is accelerating? And one of the most exciting things about this area is that we really don't know. It really is a giant mystery. Now, I'll give you 3 ideas that are in order, are probably our best guesses. The first is that there is vacuum energy. That is pretty much what Einstein had said, a cosmological constant, except this provides a more physical description of what that is. Einstein had the mathematics for it, but a quantum theory, which came along shortly after, which, by the way, Einstein was never a big fan of, actually requires there to be vacuum energy. We don't know how to get rid of vacuum energy. The empty space should be teeming with virtual particles that have exactly this characteristic, that their gravity would produce acceleration. The problem isn't how do we get acceleration from our basic understanding of quantum theory. It's how do we get as little as we have, when the theory predicts we should have about 120 orders of magnitude more acceleration than we see. That is, there should be so much vacuum energy that the galaxies, the solar system, and the Earth, none of these things would have ever formed. Everything would have been accelerated apart. This has always been a problem for particle physicists. So it still seems like there's some aspect of that problem which will ultimately lead to an explanation of why we have just the amount that we do have. I could say more about that during Q&A. Another possibility, and I should say there is even some precedent, of course, for vacuum energy. We do see fields in empty space. If you've heard about the Higgs boson or the Higgs field being discovered, this is a field, a scalar field in empty space that gives rise to mass and would act like dark energy, not the dark energy that we see, but some dark energy. It could be that we have a dynamical dark energy. That means it wouldn't be static and constant property of space. It would be transient and a time-dependent phenomenon. It may crop up from time to time in the history of the universe. And in fact, one of our most successful theories of the Big Bang involves a period known as inflation, when we think that there was a field like this, which caused the universe to accelerate rapidly just for the first, not even a second of the history of the universe. And so we could be undergoing a weaker form of one of those episodes now, or it could be that we don't have the right theory of gravity still. So, of course, we thought we had the right theory of gravity under Newton. Then along came Einstein, and we had a revision to that, which was important in different regimes. It could be that the real correct theory of gravity is different on large scales. We've never been able to test large scales before without seeing something like this. And so it could be that we don't yet have the right theory of gravity, and the phenomenon we see are just a manifestation of using the incorrect theory. But shortly after this discovery, we worried, what if we're just wrong? What if the universe is not accelerating, but our interpretation of the data has been wrong? See, when we would look at a supernova and see that it was faint, we assumed that meant it was far away. But like the case of fog, what if there was a kind of cosmic fog in space, something that theorists made up called gray dust, which could exist between the galaxies and fool us into thinking supernovae are further away than they were? Or maybe the supernovae we were seeing far out were just born fainter when the universe was younger. So we needed to test this possibility. So it was two competing possibilities: that faint meant far and that there was dark energy, or that faint meant dusty, not far. There was some kind of mysterious gray fog in the universe, and it was fooling us into thinking we were looking at things further away than they are. So it turns out that the dimming due to this dust would persist to great distances and far back in time, because if space is full of this stuff, the longer or further out you look, the more you look through it. Whereas if the universe is really accelerating because of dark energy, that must be a recent phenomenon. When the universe was younger and more compact, it would not have felt the push from dark energy because matter would have dominated the attractive gravity. And so we thought if we could find supernovae more than 5 billion light years away, we could distinguish between these two possibilities. The only problem was the telescopes we were using were not powerful enough to do that. We needed an even more powerful telescope to find the supernovae. And as I'll explain here, a little bit on the history of telescopes becoming more powerful. Here is the history of telescopic improvements in sensitivity over the eye. So here was Galileo's telescope, almost a factor of 100 times better than your naked eye. And then over the next centuries, things improved as telescopes got larger, as they moved to better locations on mountaintops above the turbulent air, replacing detectors, first our eyes with photographic plates, and then with sensitive electronics. And then we finally learned how to put a telescope up into space, getting above all the turbulent air. And I'll just show you what a difference that makes in the kind of work that I do. Here is a distant galaxy and a supernova that exploded around it, and you have to measure the brightness of that supernova. And I'll show you that same image as observed on the ground with a much bigger telescope. But it's not the size of the telescope, it's the stillness of the air, or the lack of air, I should say, in space that gives you such a clear image. And then we've been very lucky. Sometimes the astronauts return to the telescope and they put the latest generation of detectors, the most sensitive detectors, into the telescope. And so we have realized about a factor of 1 trillion improvement over the eye. So what we were able to do with that in the early to mid 2000s, after the astronauts put the advanced camera in, was we were able to find some of the most distant supernova explosions anybody had ever seen. These were objects well above what astronomers call a redshift of 1, or about 8 or 9 billion years in time, or a distance of 8 or 9 billion light years. And we were able to see, indeed, that the universe did go through this episode of slowing expansion before it speeded up. So we were able to rule out both of those alternative models, that the universe was slowing all the time, slowing enough to recollapse, or slowing a little. Instead, the universe, after going through a slowing episode in the beginning, when the universe was more dense and could feel its gravity, has now been undergoing this accelerated expansion. The universe is actually now expanding about 20% faster than it was just 5 billion years ago, due to the presence of this dark energy. So now, again, scientists are very conservative, rightly so, that everything you hear is often wrong, and any one method which shows you something surprising, there can be the devil's in the details of that method. So the real confidence in this result really occurred over the next decade, when different kinds of measurements, different kinds of experiments reached the same conclusion. I talked about in the beginning different ways we can measure distances, parallax and lighthouses and foghorns and certain sized objects. Well, we have the equivalent of that in cosmology. We have completely unrelated ways to make these measurements. So I'm just going to mention, this is probably the most technical slide that I'll have, a number of independent ways people have reached the same conclusion with different techniques. So the first was seeing the universe expanding via supernovae in 1998. In 2003, astronomers detected what's called the integrated Sachs-Wolf effect, and showed that it indicated that the universe was 70% dark energy. They looked at photons of light from distant galaxies, and when those photons traverse clusters of galaxies, these deep gravitational wells, the photons fall into those clusters, so they gain energy, and they lose energy as they climb back out. But the action of dark energy actually pries apart these gravitational potentials, so the photons do not lose as much energy on the way out as they would have were there not this dark energy. In fact, they can use this so well, they can measure how much dark energy there is, and they get the same answer that we got, 70% dark energy. Then observations of the cosmic microwave background measured the geometry of space, which indicated that the total energy density of the universe was 1 in our favorite units, the critical units. Whereas when astronomers went out and measured just how much matter there was, dark or luminous matter, they got about 30% of that 1. So again, 70% missing, same piece seen here, same piece seen here. And this was done a number of different ways, with lensing observations, a technique called baryon acoustic oscillations, mass to light ratios. More recently, we have seen the largest clusters of galaxies. These are giant cities of galaxies that are constantly pulling in more material to and additional galaxies, that even on those scales, these giant cities have been unable to pull in new galaxies, because dark energy inside those clusters is now stronger than the gravitational pull. And as a result, we are seeing an arrested development of those clusters. That was reported in 2008. In 2009, we were able to see that the change in the scale of the universe from the time that we could see the cosmic microwave background to the present, as measured in the Hubble constant, also indicates the presence of dark energy at this same level. So these are all independent, but ultimately we knew that this result was correct because we won the Nobel Prize in 2011, and they don't give you the Nobel Prize unless they're pretty sure that it's right, so it must be true. So we went to Stockholm and we had a wonderful time. Here are a few pictures from that. But after all this merriment, there was a bit of a dark side to this, as was indicated in this episode from this show called Big Bang Theory, you might have heard of. So here was one episode where they were talking about our discovery. I hope. Oops.
It's 2 a.m. What are you doing up?
Nobel Prize acceptance ceremony streaming live from Stockholm.
Sure. I want to see what all the scientists are wearing this year.
Look at these men. They've managed to win the top science prize in the world with no more understanding of the quantum underpinnings of the expansion of the early universe than God gave a goose. You should.
So we're guilty of that, guilty as charged, I would say, that we don't have a great understanding of the quantum underpinnings of the expansion of the universe. That's exactly the problem, is we are not able to go from quantum theory, which explains the vacuum, to the use of general relativity to explain how this stuff should gravitate on large scales. We see evidence for it, but we cannot explain yet how to become quantitative about the basic understanding and what we see. Nevertheless, it's pretty impressive. In the last couple decades, we have finally been able to come up with the recipe of the universe. And the recipe looks like this. Take about 0.05% planets, add about 0.5% stars, about 4% gas. So now you're up to just under 5%. And these are all the things that are made out of the elements in the periodic table of elements you learned in chemistry class. Turns out, and it's quite remarkable, that 95% of the universe is not made out of the materials in the periodic table of elements. 25% is dark matter. We think a dark particle that has a weight but does not have charge and so interacts very weakly. We're still looking for that in the laboratory. And then the new contribution is dark energy, which makes up about 70% of the universe. So the glass is sort of half full, half empty. Half full that we have figured out what the universe is made of. Half empty, we don't understand most of the stuff that is actually in the universe. But we're still working on this. Very fortunate. The astronauts returned one last time in 2009. They put new cameras into the Hubble Space Telescope, which has allowed us to improve the way in which we can measure dark energy. We've already realized an improvement in the measurement of the Hubble constant. We've been able to find even more distant supernovae back from a time long before the acceleration began. And so we continue work like that just to show you how fantastic it is when you get a new camera from the astronauts. Each camera is usually much more sensitive than the previous one. So here's a 48-hour exposure. We kept the shutter open for 48 hours on Hubble using the old near-infrared camera. And then here is the new camera in just 10 hours. So if I jump back and forth, look at the very faintest objects that you see you're going much more deeply with the new camera. And it only took 1/5 the time, and the new camera has 100 times the field of view. So this really, no pun intended, accelerates our ability to do the science of the accelerating universe. And so we've always been very grateful for that. Also, the space agencies, NASA and the European Space Agency, are right now developing plans for next generation space telescopes that are largely driven by efforts to measure dark energy. So in 2010, the National Academy of Sciences Decadal Survey picked this dark energy mission called WFIRST as the #1 priority. The European Space Agency in 2011, the same thing. And in 2012, the National Reconnaissance Office in Washington that makes spy satellites gifted 2 almost done telescopes to NASA for the purpose of doing this. And so we hope in the next decade, both of these missions launch and that they can provide vital clues about the nature of dark energy to tell us, is dark energy changing? Is it evolving? That's part of the story of whether it's Einstein's cosmological constant or whether it's one of these fields that come and go, or does Einstein's theory even work on the largest and intermediate scales? That will tell us if there's a scale-dependent flaw in Einstein's theory. So I just want to end with a reminder, why is it that we study dark energy? Well, first of all, it's most of the universe. So it's pretty hard to say we really can ever understand the universe if we don't understand what is the biggest chunk of it. My colleague has likened this to not understanding water when our planet is 2/3 covered with water. If you were born inland, the first time you came across water, you would want to understand what it is. It will determine the fate of the universe and may tell us a lot about the origin of the universe because it is the dominant force today. And so we have to understand it to understand if the universe will continue to expand forever, whether the universe as we know it is a sort of one-shot deal or whether it's still possible that it's a cyclical phenomenon. But most important, I think, is that understanding dark energy lives at the nexus of our two most successful theories in physics, quantum theory and general relativity, but two theories that are intrinsically incompatible. And so one of the best ways to learn how to unify two theories is just watch nature do it and see if we can get a clue from that. Right now, we're way far off. There are different kinds of efforts underway now to unify these with varying success. So the thought is we should follow the dark energy and it will lead to something interesting. So I will end there and take any questions that you have. Thanks. Yeah, go ahead. So the Hubble Space Telescope is oversubscribed by about a factor of 10. So that means we get 10 times as many applications or requests for 10 times as much observing time is available. It's a pretty daunting challenge to get time. I mean, you could say, okay, a third of the applications are not great ideas, or certainly you could write something better than that. But, even the top half are very good. And it is frequently said you could do much, much more science with more of them. When the time allocation committee meets and decides, even though they prioritize what will be in the top 10%, they still draw a much lower line of things that should be done or things that are good uses of the telescope. We do that because if some strange event occurs, one of the instruments fails, and we need a whole bunch of programs on the particular instrument that works, we need that list. But it also just impresses you how much good things there are to do. And this is still in the 25th year of Hubble. So I think, it's pretty tough. I've been lucky. I've been able to get some time from time to time, but.
Are your observations from some of those mathematical theories that what's your favorite parameter?
Right. They are, because with supernovae, we could observe over such a wide range of redshift. That is, we could observe such a wide range of times in the history of the universe. Out of a universe that's 13.4 billion years old, we have seen supernovae as far back as 11, maybe 12 billion light years. So we have the ability, in principle, to see how things change and whether dark energy is constant. But the problem is, when you go that far back, dark energy is so subdominant that you're measuring a smaller and smaller effect, and you're trying to understand the properties of something that is diminishing. And so, although we can go back to the time when we need to, our leverage is dwindling. Nevertheless, we have been able to say that that dark energy, let's see, the latest results were, we could say back about 6 or 7 billion years ago, when dark energy was subdominant, it still hasn't had an equation of state that was similar to the cosmological constant. That is, dark energy looked like dark energy even 6 or 7 billion years ago, even before it was overwhelming dark matter. But we want to reach much greater precision than that. The goal is to be able to measure this quantity known as the equation of state of dark energy to about 1%, and the time rate of change of that to about 10%. That would represent about 100 times better than what we have measured today. And we think we can do that in the next 10 to 15 years with some of these facilities that I talked about. Sure. Dark matter is very different than dark energy. I mean, the thing they have in common is neither of them emits light, and we infer both of them by their gravity. So we see the gravitational action of both of them. But then dark matter clumps. It clusters in places where matter clusters. So there's excessive dark matter in galaxies and in clusters of galaxies. Dark matter is also not very dense, which is why we don't feel its effects on the Earth or in the solar system. But as you look at larger and larger volumes, the luminous matter becomes more and more diluted. The average density due to luminous matter is huge in this room, is huge throughout the Earth, is much lower in the solar system, is still much lower in the galaxy. And so if dark matter is uniform, eventually you get to a scale where where there's more dark matter than luminous matter. That scale is the galaxy. So on the scale of the Milky Way galaxy, there's about 10 to 20 times as much dark matter as there is luminous matter. And so the effect we see is stars are whizzing around the center much faster than they would if there was not this dark matter. The stars would be taking off. Same thing about galaxies moving around clusters of galaxies, that clusters would not be able to gravitationally hold on to galaxies were it not for this dark matter. So we see dark matter cluster, we see the evidence for it, but it's a very different phenomenon than dark energy. We can tell some. We can tell how it clumps. We are, as I said, trying to actually detect the particle collisions of dark matter with normal matter, but they're very infrequent. So, and you have to, they get these big vats of chlorine or argon and put them in mines that are below the surface of the Earth to shield out all the other particles. And then they open up these boxes, or xenon, I think, is the one they used most recently. But it's been difficult because the interactions are very weak. So accuracy and precision are two different things in this context. Yeah, so the accuracy gets down to how well you can calibrate the flux in a telescope that you observe. So what kind of standards do you have? And so I would say we can do that to about maybe 1 or 2%. And since one supernova measures to a precision of maybe 5 or 10%, samples of 100, we're still above the systematic error limit. But once we get to 100 or more, then we have to start doing better on the calibration. We do see scatter in distance. That's what we call the intrinsic scatter of type 1a supernovae. And that may be because they're not all perfectly round. So the face that we're seeing is not, perfectly isotropic. It may be that some white dwarfs, before they explode, are rotating fast, and that can hold them up from undergoing the thermonuclear explosion. So they may explode at a slightly greater mass or a weaker mass. All kinds of things like that do cause differences. There's different opacity, different temperature histories of their layers, which means that more or less energy might be trapped in the explosion. They could reach a greater peak luminosity. We use empirical relations to account for those differences, but even still, there are some differences. That's a great question. Why does space only expand between galaxies? That's actually not true. We think that space would expand everywhere, but because inside galaxies, matter is so close together that it can hold on to each other through gravity. Think of like if you had expanding ice, let's say, and you were standing on the ice with a friend, you could be pulled apart, but if you held hands, the expansion would slip or slide under your feet. So galaxies or planets in our solar system, they are so gravitationally glued to other things that they don't feel the expansion. They just slide along. They have stronger binding than dark energy. Good question. Yeah, you can do a lot with adaptive optics from the ground. I've never been that impressed with what adaptive optics have done for measuring precise fluxes. So, generally you shine a laser up and back down, you measure the change to the distortion in the laser, you put that into your telescopic image, and what generally happens is you get a lot of light in the central beam, the STREL, but you don't really know how much light has been lost to wings of the point spread function. So we need very precise and accurate photometry, measures of the brightness. And so I think adaptive optics are good at separating objects, giving you resolution, but not necessarily precise flux. Oh, I see what you're saying. Yeah, that's small. Very small. I mean, those are, a heavy cluster of galaxies might be, 1,000 or 1,500 kilometers per second. Once we are dealing with these distances, we're seeing redshifts of, hundreds of thousands of kilometers per second or more. Yeah, so looking and seeing the properties of dark energy different in different directions. Yeah. Right. The good news is that's an easier measurement, because to compare a supernova in this direction or this direction, this issue of flux calibration really goes away. You're measuring things in the same band, so you don't even have to know that. The bad news is theorists tell us that if the dark energy is something like one of these fields, then the variations they expect place to place, they sort of expect a part in 10 to the 4, 10 to the 5. So part in 100,000 is going to be awfully difficult to measure. So the way you make the measurements is easier, but the challenge is so much greater that I don't think that will be the first way we detect that dark energy is not a cosmological constant, that it's a field. The end? You want to know when? Do you have a mortgage? Yeah. Oh, well, there's the visible aspect. So if the universe accelerates, there will come a point in time where there's not enough time left or not enough speed for light to get to us from distant objects. So the horizon, which normally grows as time, will start to shrink. And in fact, eventually we will not be able to see things that are not gravitationally bound to us. We will only see Andromeda and a couple other galaxies. That's the visible part. The reality part is, well, it really depends on what the nature of dark energy is. If it is the cosmological constant, then the universe will accelerate forever. Things will get far apart. Of course, galaxies will stay intact. But eventually galaxies run out of energy, as all the useful energy products are locked up in black holes or cold black dwarfs. But it is also possible that dark energy can morph. If it's a field, it may decay, and it may decay to a vacuum state, a ground state, which is actually below zero. And if that happens, then it can become an attractive force. And if that happens, then as long as the universe gets big enough, then you get more attractive gravity than you ever wanted, and so then the universe recollapses. So we have to actually better understand the nature of dark energy before we can make really long-term predictions.
One last question.
Right. Well, one of the things that we see, and this is really interesting, is we observe nearby supernova explosions, and they have a particular life cycle that is very well calibrated. They go up at a certain rate, they go down at a certain rate. In 15 days, they've dropped by a factor of 3 in brightness, all that stuff. When we look at the distant ones, because the redshift is due to expansion, you get time dilation as a result, right? And indeed, we see that distant supernova explosions have time dilation, exactly the 1 + z factor that you expect. And so we can either take observations of the spectra of supernovae, which we can age date to how long after the explosion, or we can just watch the whole light curve history. But we are able to observe time dilation, which is a feature of expansion and not a feature of other interpretations like tired light or other things.
I'd like to present this plaque to Adam for giving a wonderful Thomas lecture, and let's thank him one more time.
Thanks.
Thank you all for coming.
Well, it's the